action instead of
Hello? Hello? Can anybody please respond? Dr.
Yes,
Tiwari?
sir.
Yeah. I think Professor Yadav again lost connection. Professor Tiwari, I can go ahead?
Yes, sir. Please start. Actually, there is net connectivity problem at our end, but please start.
No issues, no issues. Yeah, thank you very much. Thank you for the invitation. And Professor Yadav, the head of the department, Professor Tiwari, the coordinator of this program. And it's really a pleasure to be with you in this morning, today morning. And I don't know, we are celebrating Sharad Purnima today here. So wish you all a happy Sharad Purnima and namaskar. So, yeah, this is, I had never been to this institute, but as Professor Yadav said, hopefully, if I survive this COVID, I will definitely visit the institute. And I have some good friends in IIT Kanpur. I have a good friends in Lucknow. So one day I will definitely visit them. Yeah. So as Professor Tiwari mentioned, we have been working on IoT, sensor network, and other things. And I have been asked, and I also told that what is the research that is going on in this field very recently, the advanced research going on in this field. And then we'll also discuss a couple of things what we do in our lab here. And maybe some of you who are doing research or planning to continue research in this domain, I hope you will be excited. Some of the neurons will be excited in your brain so that you can also plan to do some research here. So let me share the slides which I prepared for this presentation, and then we'll discuss one by one. Yeah. So I think the slides are visible, right, Dr. Tiwari?
Yes, sir. Yes, sir. Yes, sir. Slide is visible.
Very good. So, in fact, although I'm supposed to talk about the basic advances in IoT and other things, instead of that title, I chose the title Internet of Things and Deep Learning. And we will be also discussing a couple of applications that we have developed here. And maybe if you are interested, we can also continue to collaborate and work on this actually. So I am Siba Udgata. I work for School of Computer and Information Sciences, University of Udgata. And very recently, not very recently, almost a year back, we have been conferred with the status of Institute of Eminence and by Government of India. So we've been doing good, and we are planning to move ahead with the ranking, and the university as a whole is planning to be within the top 500 universities of the world. So having said that, we have a lot of responsibility also, and our vice chancellor, administrators, etc. We have been working towards it, and we are setting up some labs, buying some instruments so that we can do a lot of work, lot of research, which requires high-end computing, which requires high-end instruments. In this scenario, of course, this talk doesn't talk about that, but this talk will definitely talk about what are the advances. So, for example, in the last 2 days, Professor Tiwari was mentioning, you might have known about what is Internet of Things, how sensors are working, how they are connected, how the data is being sent, and all these things. So, I will not be talking about that. I will talk beyond that actually. So, if you look at deep learning, deep learning is a machine learning tool. So, Internet of Things actually generates a lot of data, huge amount of data. Now, what do you do with the data? What kind of information? So, what kind of information you can derive? What kind of decision you can derive from it? What kind of learning you can derive from it? What kind of knowledge you can derive from it? So that is the key actually. And some of the things which are not possible, not computable at few years back, because of lack of data, because of lack of computing power, etc. Now it has become possible. So it is not that all of these things are coming up fresh, but some of these ideas were there, but those ideas were not worth pursuing because we didn't have the support system. We didn't have the lot of computing power. We didn't have a lot of sensors. So now we have those things, and then we can go beyond these things. So if I look at some small ideas, so of course we have to talk about a machine learning a bit, because machine learning is the key by which we collect data and then learn different things. So IoT gives me the data. Now what I do with the data, I have to do with I have to know the machine learning, etc. So the basics of machine learning is that, of course, some of you who knows machine learning, this is very, very preliminary. But some of you who do not know, I'm just saying that I'm not trying to teach you machine learning, but what I'm trying to do is that I'm trying to introduce machine learning so that you can go back, Google, read papers, and then learn about it. So machine learning is a field of computer science that gives computers the ability to learn. May I request all of you, please mute your hello.
Please mute your video. Participant, please mute your video. Otherwise, I will immediately remove. Just I am checking. I will immediately remove. Neha Singh, I am just removing you. Neha Singh, I am removing you.
So sorry. So the ability to learn without being explicitly programmed. So for example, the traditional programming requires an input, requires a program to give an output. Now in machine learning, the traditional programming is slightly changed. You give the input, you give the output. You give the input, you give the output, and the system will learn a model, learn a program, or create a program on its own, so that similar input will give the similar output. I repeat what I said. In a traditional programming, you give the input, you give the method or the program, and the output will be generated. In machine learning, what happens, there is a slight change. Please mark my words. You give the input and you also give the output, provided given this input, what output you are expecting. Now, the system, the machine will learn how to generate this output from this input. So we are not explicitly programming, giving the method. We are giving the input, we are giving the output, and asking the machine to learn that for a similar input, you should provide similar output. So how do we do that actually? So this is a slightly different from the traditional programming, and that's a paradigm shift. So the paradigm shift here is that I give an input, I give the desired output, and the machine will learn how to generate similar output from the similar input. That's the key. So what I do here, if I look at the figure here, so I have level data. So the data is the input, level is the output. For example, you take my image, face image, and level it that this is Professor Udgata. You take Dr. Tiwari's image and say that this is Dr. Tiwari. You take a dog image and say it's a dog. You take a human image, you say it's a human being. You take a cat image and say it's a cat. So these are all levels. The machine learning algorithms will learn how to, so given the input, a cat input, how to classify it as a cat. Given a human image, how to classify it as a human being. Given a robot, how to classify it as a robot. So the algorithm will learn it. Now, if you have a data which is unlabeled in the sense that you don't know what is that actually, you give that data. For example, you take a photograph and show it to the system. The system, using the learning model, will try to generate what is the output. So what I'm saying, I give you the input is the human image, dog image, cat image, car image, truck image, and ask the algorithm to learn to create a model such that similar output will be provided given the similar input. So now I give an input for which the output is not known. This same model will be used, and you will be able to predict what is this actually. So that's a basic thing what we do in machine learning. Now, what is deep learning? Deep learning is also a machine learning algorithm, but now deep learning has become so big, so huge, so powerful that it has become a subject by itself. It has become a domain by itself. So what is the basic idea? Because I don't want to spend more time on this. The basic idea is that in a standard machine learning environment, people who have done machine learning, they understand that I give an image or the data. From the data, the human being, or there are some algorithms which will find out the features. Now, what is a feature? For example, you give a face image. The face image features are big eyes, long nose, fair complexion, ear, there is a, your chin. So all these things are your features. Your spectacles. So if you are using spectacles, then your spectacles. So these are the features. So from the image, face image, you derive features, feature extraction. Similarly, from a car image, you derive that there are wheels, there is a bonnet, there are seats, there is a steering. So these are the features. So once the features are extracted, you are not giving the raw image to that, you are giving the features. So once the features are extracted, any neural network or machine learning algorithm will try to classify and try to find out whether it is a car or not a car, whether it is a face or not a face, whether it is a dog or not a dog. So what do? We take a data, or we take an image, we take a voice, we extract features from that. These features are given to the machine learning algorithm so that it will try to classify what kind of image, what kind of data it is. But in a deep learning, interestingly, and why it is very powerful also, the deep learning is that key. In the deep learning model, you don't require a human being, or you don't require a human assisted learning to extract the features. You just give the image. The image, the deep learning model will automatically extract the features. So look at this. This is feature extraction and classification together. So the deep learning will find out feature extraction plus classification. So it doesn't, you don't require a separate human assisted technology for feature extraction. Then the features will be provided for the classification algorithm. That is not there. So one of the major difference between the deep learning and multi-layer neural network is that, or deep neural network and multi-layer neural network is that key. In a multi-layer neural network, we have multiple layers, but the purpose is remains same. But in deep learning, the purpose also changes. Now, if you look at this, why deep learning is very useful, because if you have a lot of data, the standard machine learning algorithms or the neural networks, support vector machine, etc., they don't go, or their performance doesn't increase beyond a particular point. So if you have a small amount of data, they reach around, let's say, accuracy of 90%. Even if you give a large amount of data, the accuracy doesn't increase beyond 90%. So there is a plateau, there is a saturation. But in case of a deep learning, if you have more amount of data, the accuracy tends to be more. Of course, it doesn't go beyond 100%, but accuracy tends to be more. So now people who are struggling with character recognition, with image recognition, with voice recognition, etc., with a accuracy rate of around 80, 85%, 75% to 85%. Now, the moment deep learning came in, suddenly the accuracy increased beyond 90. Now, anybody talks about 95% accuracy, 96% accuracy, 99% accuracy, which was a dream 10 years back. So since 2015, as I told you, since 2015, the deep learning started outperforming other ML techniques. So be it in speech or vision or then many others. So we'll also see in IoT how these things are done. So this is basically deep learning. Now you see the whole idea is that the multi-layer neural network have been there for around 25 years. But now only in the last 5 years, the deep learning comes into the picture. So usually people who have worked on this 20-25 years back, there is only one hidden layer, and this is the input layer, this is the output layer, and there is only one hidden layer. But suddenly people thought that one hidden layer is not good enough, let us make it multiple hidden layers. But the complexity increases by quite a lot, but the performance doesn't increase the way we expect actually. So that is why people in neural networks, etc., or in standard machine learning algorithm, etc., they thought that okay, by just increasing the layers is not good enough. Then why deep learning has
sir, just interrupting, sir. One participant is saying, please return to previous PPT for 1 second.
Here?
Yes.
Oh, okay.
Yes, yes.
I thought I will not. Okay. Oh, thank you very much. Thank you very much. And keep telling me, keep reminding me if there is any, because I'm not looking at the chat now. It's a full screen mode, so I'm not looking at the chat. So what exactly is deep learning? Why is it generally better than other methods on image, speech, and certain other types of data? Multi-layer neural network have been there for 25 years. What is actually new? So the quick answers, I'm saying the quick answers here is that the deep learning means using a neural network with several layers of nodes between input and output. So that is similar to multi-layer neural network. But what is the difference also you have to see? A series of layers between the input and the output, do the feature identification, do the feature extraction, and also process in a serial of stages, just as our brain seems to do. I mean, there is a paper in 1962 published in Nature. That's where they initially said that this is how it works. But I'll just give me a minute time. The next slide is also about that. So, but these algorithms are not good enough. So I repeat here. these algorithms are not good enough for learning with more hidden layers. Even if you increase the number of layers, the algorithm that we are using for neural network, etc., was not good enough or not proved to be good enough, even if you increase the computational power to a greater height or greater level. So the idea is that what is new? The new is that they thought of a new algorithm altogether. So it is not that the same old age-old learning algorithm will help us. They created a new algorithms. For example, convolutional neural network algorithm. So those algorithms are the key. So it is not that only the multiple neural networks, multiple layers. It is the algorithm, and also it is the way you train them. That's the difference. So look at the next slide actually. So as I told you, deep learning doesn't do different things. The same thing what we have been doing. For example, speech recognition, we are trying to do image processing, we are trying to do audio synthesis, we are trying to do all type of data, weather forecasting. All these things we're using machine learning techniques. Now deep learning also does the same thing. It doesn't do the different things, but it does things differently. That's the key actually. So if you look at this, what is the new way to train the multi-layer neural network? Earlier, what was happening? The input will be given here, right? And the output, the input will be multiplied by the weights, etc. It will pass through this, and this. Now we find out what is the actual estimation and what is the desired error here, desired value. Now the desired value and this error, so you get an error. Now this error is now used to train these models. So train the weights and then train modify the weights. Now that is what a simple multi-layer neural network does. But what happens in a deep neural network, it doesn't do like that. It tries to, now look at this, train these two layers first. That means the input layer and this layer. So this is, train first these two layers. Once this training is over, go to the next two layers. Then go to the next two layers. Then go to the next two layers, and then go to the next two layers. Now, finally, what I was trying to say, if I go back, in the previous, in a multi-layer neural network, it's a one-pass training. So I keep training, I give the input, I get the output, I find out what is the desired output there or what is my required output. There is some error. That error is back propagated or propagated back, and then we change the weights, and this goes on for hundreds of thousands of iterations. And then you get the weights in such a way that given this input, the desired output will be as close, or the estimated output will be as close as to the desired output. But this model is changed in the deep learning, where it says that no, don't worry about the output at the first stage. First you go for the first two layers, then go for the second two layers, then go for the third two layers, then go for the fourth two layers, and so on and so forth. So finally, what happens before the output reaches before the input reaches the final output, the intermediate layers have already been trained actually. So this is one important feature of deep learning, that we are not training the entire network at a time. We are training in layer wise. Although there are multiple layers, 25 layers, 30 layers, 40 layers, but you are not training all the 40 layers at a time. So this is the key actually. So what happens here? So the intermediate layers are each trained to be autoencoders. Autoencoders means, see, in this example, I have seen that three inputs are there, here three inputs are there, here also three. But it is not necessary that all the layers will have the same number of inputs. For example, the input layer, let's say there are 1,000 inputs, right? And here we have only 100 inputs, 100 neurons. So what will happen? This 1,000 will be converted to the 100. Now the 100 means what happens? Suppose in a face, in an image, you you take 1,000 pixels, and the 1,000 pixels you convert to 100 features. So those features will be lines, circles, color, texture, etc. So what happens is that it converts the original data into a autoencoder kind of a principle, or a similar type of principle. What is that I'm trying to say? Again, I repeat, the number of neurons in each layer need not be same as the input layer. So what happens actually, now you take 1,000 layer, then you take 100, then you take, let's say 50, then let's say 25, then let's say 10, and finally 1. So what happens here? 1,000 input you give, that 1,000 will be converted to 100 in the next layer. That means it is encoded, it is compressed. It extracts 100 features out of the 1,000 features. Now the 100 will be converted to 50 in the next layer. That means the 100 will be now converted to 50. So how do you say? For example, I say that there is an elliptical face, elliptical circle, and there is a small arc, then that is an eye. So that those 3-4 structures, geometrical structures, is converted to an eye. 1 or 2 geometrical features will be converted to a nose. So that means what? These 100 features of lines, circles, arcs, etc. will be now converted to 50 features. The 50 features will be converted to 25 features. So what happens actually? Initially, you give a lot of input, but the inputs will be converted to feature 1, feature set 1, feature set 2, feature set 3, and finally you get your output as a one output. So this is a model which we say that it's pretty much there in the deep neural network, but it was not there in the multi-layer artificial neural network. So that's what. Finally, the layer is trained to predict the class based on the output from the previous layer. So we are only looking at the output actually looks at the previous layer. So it is as good as at the last layer, it is as good as the artificial neural network. But before that, it has all the feature extraction processes, which was not there in the multi-layer neural network classes. Now, this is what I've already said, the performance versus sample size. In a traditional machine learning algorithms, or in case of neural network algorithm, etc., even if you increase the size of data samples, you have lots of data samples, but the performance increases initially, but then after some time it becomes a plateau, it becomes stable, it doesn't increase. Even if you give a lot of data, you collect a lot of data, but your performance doesn't increase. But deep learning algorithm had the inherent capability of increasing the performance when the data size is increasing. After that, it becomes like this, right? So your performance earlier, all the machine learning algorithms were stuck at 75%, 80%, 82%, 85%, etc. Now they have increased up to 90%, 95%, 98%, etc. So that's but the key is that you have to have a lot of data. Now, where you get the data? Now, these IoT sensors, cameras, so many data samples are available. Earlier, getting data was also a problem. Now, so much of data is there, and this data gives me a scope to apply an algorithm which will give me a lot of other features. Now, this is what I want to tell you, because I didn't talk about deep learning as such, because I have a lot of other things to talk about. What is the basic idea of deep learning is that the whole problem with the deep learning is that people who have started working or want to work, the problem is that there are multiple layers, right? Suppose there are 30 layers. In 30 layers, there are 30 different type of learning algorithms. In each learning algorithm, you have different type of thresholds. You have different type of bias. And there are so many weights to be trained and all these things. So it involves millions, sometimes even billions of parameters to be tuned, right? So if I am a new to machine learning or deep learning, etc., and I have some application, let's say I'm from mechanical engineering, from civil engineering, from electronics engineering, I have so many applications. Now, I'm not a very good at deep learning and all these things. Tuning billion parameters or millions of parameters so that you get your output correct is not easy. So what is that we are trying to look at? We are looking at a concept called transfer learning. What is transfer learning? You learn in one domain and then transfer that learning to the other domain. For example, I think this is one of my favorite example, and many of you might be knowing, the Indian cricketer MS Dhoni, right? He was originally a football player. Actually, he was a goalkeeper in football game. And one day, many people might be knowing this story. One day, there was a cricket match, and the wicket keeper didn't turn up. So the coach looked at MS Dhoni and asked him that you come and keep the wickets. Now, what happened is that because he has that learning of keeping as a goalkeeper in the football, he just transferred the learning. He didn't learn wicket keeping actually. He just transferred that learning to wicket keeping in cricket, and he was quite successful then, and rest is history. So the whole idea is that the transfer learning is that if you train a model, let's say we train a deep learning model, a deep learning architecture, complete architecture in some domain, in some application, or in a related application, the training is done. Once the training is done, now I have a new problem. So what I do, I don't start training from the beginning. I start training from the trained network. So what has been done so far is that the researchers have worked on the architecture and suggested few trained deep neural architecture. It's already trained. So they have trained it, they've spent years together, they've published papers. So those 1 year or 2 years of work of training billions of parameters is now they have trained it as a AlexNet, VGG 19, ResNet 50, MobileNet, Inception V3. There are so many, SqueezeNet, there are so many things, so many architectures are available now. What is this architecture? This architecture means in Python or in MATLAB, we have a code, we have a library. If you want to use AlexNet, just use AlexNet, the entire code in the sense trained code, trained weights, etc., is now inherited into your code. Now what you do, you give your data to AlexNet. It is already trained, and then it will start giving you the output. If you are not happy with the output, a small fine tuning is required, which can be done within 15 minutes or within half an hour. But if you don't have the trained network, probably you have to spend 6 months of time to train the network for your data. So now, what is the transfer learning? A learning happened with other researchers. They learned by doing experiments, doing simulation, etc., for a long time. So for different type of problems, now different type of learned networks are available in Python, in MATLAB, and other things. As an user, what I have to do is that, okay, I will use one of these architecture and try to see with my data what is that I'm getting. And then I can see that, okay, which type of network is suitable to me, and I can do a small fine-tuning, corrections, etc. So that's what I'm saying. You can use that learning experience and use it in other applications. So this is very important, and I urge the participant that whosoever wants to do it, please look at the learned networks, already learned networks, and then use it in your application. Okay. Now this is, I mean, this is what a small introduction about deep learning, a very small introduction, and there are, I think, hundreds of hours of video lectures are available in the internet, etc. If it excites you, please go Google, go to YouTube, and then try to read more on that, do your hands-on on that and everything. Now, one of the important activity or important research that is going on in this domain now, in IoT and sensor network domain is now, how do I sense without using sensors? Or for example, I have given a title here, a deep learning model for human activity detection using Wi-Fi signals. You know, Wi-Fi routers, Wi-Fi signals, and all these things. So this we'll see a little more than that. So as of now, you have seen a lot of classes now, and you had listened to other experts also. So you know that Internet of Things consists of sensors, the edge nodes, the server, sink or cloud, and then the wireless communication. So these are the basic 4 important pillars of Internet of Things. We require sensors to sense different physical parameters, environmental parameters, health parameters, etc. So the sensors have to be deployed. That's what I call the deployment. Or the sensors can also be wearable. You wear the sensors. Now the sensors, there are issues. Reliability is an issue. Drift is an issue. Drift is an issue. Drift in the sense that today the sensor will give some value. After 1 year, the sensor will give some other value. So we require calibration, automatic calibration, etc. And with drift in the sense that, you know this, for example, you go to a weighing machine, right? A digital electronic weighing machine. You see that there is a value. Now what they do, suppose the value is 10 or something, they press a button so that this initializes. So what is drift? Drift means with 0 input, the output should be 0. So in a weighing machine, there is a pressure sensor. So when the pressure is exerted on that, the pressure sensor gives a value, and that is converted to the corresponding weight. Now what happens in a drift is that with a lot of use and other things, the 0 input will not give you 0 output. So 0 input may give you 5 grams or 5 milligrams or 5 grams, like that. So that drift increases with time, and that has to be compensated. So that's an issue with every sensor. The values gets drifted with time, and the drift correction has to be done. The other important problem with sensor is that cost versus precision. If you want to measure temperature, 25 degrees centigrade, 26 degrees centigrade, etc., the cost is less than 100 rupees. But if you want to measure temperature with 25.1, the cost becomes 1000 rupees. If you want a temperature sensor to measure up to 2 decimal places, for example, 25.01, 25.02, etc., accurate up to 2 decimal places, suddenly the cost becomes 1 lakh. If you want up to 3 decimal places, it becomes 1 crore. So that's the problem with the sensors actually. If you want a real precision, a very less least count, then the cost increases. What is an edge node? Edge node is the node with computing power, with battery, with sensors, which is there at the site, deployed at the site. That's a complete node. It's a computing node. So the node contains multiple sensors, node contains communication devices, node contains power, node contains storage, everything. So that's a mini computer that is there deployed in the field. What is the server or sink or cloud? The data that comes from the sensors through the edge node will push it to a cloud or server or a sink. How did it push us? Using the wireless communication. For example, Bluetooth, Zigbee, Wi-Fi with 2.4 gigahertz, 5 gigahertz. It can be also cellular communication. All those things are there. So the 4 pillars of Internet of Things is sensors, edge nodes, servers or cloud, and the wireless communication. In this talk, we'll talk about how do we go about what you can do about the communication part of the Internet of Things. What I'm talking about is that this work people have started in MIT, USA, Massachusetts Institute of Technology, and then some people in Washington University are doing it. Very recently, City University of Hong Kong has started some work on this. Now we have also started in India. I don't know other places where they are doing it in India or not, because so far they have not published yet. So once they publish, we will come to know that whether they are doing it or not doing it. So what happens is that the sensor-based activities recognition is that say the problem here, what I'm trying to talk is that a human being will the activity of the human being, for example, falling down, jumping, waving, running or walking. So these activities we should be able to detect. One is that we have camera based actually. So you put a camera like your CCTV camera, etc. Then you take the video feed, and video feed will be analyzed to find out what is the activity of the human being there. But those are issues. They cannot be used everywhere. I mean, we'll see about that. So sensor-based activity recognition is that accelerometer sensor. What is an accelerometer sensor? It will detect or it will measure the change in the x-axis, the linear change in the x direction, y direction, and z direction. So accelerometer sensor will try to find out your movement or change in the x-axis, y-axis, and z-axis. Gyroscope sensor will find out the change in the angular direction, theta x, theta y, and theta z. Camera sensor, I just told you. Wearable sensor like your Fitbit, etc. You wear it, and then that is also collecting the data. Cloud and server-based analysis means all the data will go to the cloud and server, and there people analyze to find out what kind of activity this guy is doing. So some of the examples which I'm saying is that smartwatch, Fitbit-like devices, smartphones. Smartphones also try to measure your number of footsteps you are walking and all these things. So what is that I'm trying to say? You can recognize the activity of a human being using some sensors. Now the next, what is the challenge? Why it is not very popular? First is that if you try to use a wearable device, etc., convenience is a big problem. My mother doesn't want to wear a device around her neck and all these things, or always carry a phone when she goes to toilet or something. So it's not very convenient to use. Acceptability, many people are not, they have own perception about their devices actually. Many people feel that, oh, no, there is a radiation, I don't want to keep it close to my body, I don't want to put it in my front pocket. So there are acceptability is a big issue when you put a device into the body. So for example, we have been working with a project with IIT Bhubaneswar for monitoring the health of the baby when the baby is in the womb for a pregnant lady. Now, what you have to do is we designed a belt kind of a thing. Of course, they designed a belt kind of thing, and I put algorithms into that. So the belt has to be, you have to wear the belt. The lady has to wear the belt around the stomach area so that the body, the baby's movement, etc., can be monitored. But people didn't accept it. People didn't accept it, and they thought, it will have some effect on the baby and all these things. So that's what I'm saying. The perception also matters. Affordability, many a times the cost is very prohibitive. The sensors are costly and all these things, so you will not be able to afford it. Availability, even if somebody can afford it, but it's not available also. So large scale availability is also a challenge. Most importantly, privacy. If you put camera, if you put all these things, people feel that somebody else is watching me. Why should I allow them? Privacy is not about only you want it or you don't want it. There are cases where the privacy is important. For example, I want, when my old parents go to the restroom or toilet, I don't want them to close the door because they fall down and all these things. Now, I cannot put a camera inside the toilet to detect whether they are falling down or not. So there are issues. I cannot put a camera CCTV in my bedroom. I cannot put a camera in my drawing room because that's a private place. So can we have some other technique based on IoT so that we can develop acceptable, available, and affordable things? So people should accept it, things should be available, and it also should be affordable. What is this actually? And I hope you give me some 5 minutes and I seek your attention on this, because once you understand this, everything, all other slides are just results. What is Wi-Fi sensing? Wi-Fi sensing is basically sensing without sensors. There is no sensor. There is nothing attached to your body. There is no separate sensor that you have to buy. What is Wi-Fi? Now imagine that just listen to me. Imagine that in my house there is a 2.4 gigahertz Wi-Fi router. So the Wi-Fi signals are there in my entire house. Once the Wi-Fi signals are there in my entire house, the new technology that can you use the signal characteristics to sense the activity, to sense the environment in my house. What is the idea? The idea is this. The idea is that there is a Wi-Fi transmitter and there is a Wi-Fi receiver. I'm simplifying it initially. So there is a Wi-Fi transmitter and there is a Wi-Fi receiver. Now look, in my home where I'm talking now, let's say there is nobody there, and there is in one corner there is a transmitter, in another corner there is a receiver. Now the signal is going from the transmitter to receiver. So there is a lot of the signal gets propagated in 360 degrees, and it goes, hits the wall, gets reflected. So there is a reflection, refraction, all these things happen. So the receiver will receive the signal. Now when the receiver receives the signal, there is a characteristics of the signal, the amplitude, the phase, the so many things are there. Now in a blank, in an empty room with all these furnitures, etc. there, so there will have a lot of reflection, etc. And finally the receiver receives the signals and characterizes them. Now let's say a person walks in. Now when a person walks into the room, the signals will start reflecting from its body and all these things. Now that means there will be a change in the characteristics of the signal at the receiver also. Now if I use a deep learning method or a machine learning method to tag that, okay, a person has entered into the room, and this is the change in the receiver signal. So the change in the receiver signal, I label it as a person entered into the room. Let's say a dog enters into the room. Let's say I come and sit in my office chair. The moment I sit in my office chair is at a particular corner of the room, and the reflection pattern, the signal reflection pattern, etc. will change, and the characteristics of the receiver signal will change. So if I say that I label that signal as a person sitting in the chair, or the professor sitting in the chair, that I label it. So subsequently, if I say that when I go and sit in the chair, looking at the change in the signal pattern, I can identify that, okay, the professor has come and sat on the chair. That is the basic idea. So what is the basic idea? The Wi-Fi transmitter continuously transmits the signal. We will use a receiver which will receive the signal and find out the characteristics. Once the characteristics are found out, we will conduct a human activity like jumping, sitting, etc. Now when you conduct the human activity, there will be a change in the receiver signal characteristics. That receiver signal characteristics, we call it as a CSI value. CSI means not Computer Society of India. CSI means channel state information. So every Wi-Fi communication happens in a particular channel. The channel state will give me the amplitude, give me the phase and all these things. So that information, if I can capture, the channel state information will continue to change if there is an activity between the transmitter and the receiver. Now, because this is omnipresent, the Wi-Fi signals are 360 degree. Wi-Fi signal can also penetrate walls. So there is a research going on now that how do I see or how do I know what is the activity that is going on across the wall? Because the signal that is coming out from within the room, if there is a Wi-Fi transmitter within the room, that transmitter that signal can cross the wall and come to the receiver outside the wall. Now that kind of research is also going on. So what is that I'm trying to do? What we are trying to say is that Wi-Fi sensing is that it's a new technology that enables motion detection, gesture recognition, and even biometric measurement. People are now trying to say that when you are sleeping in a room, the sleeping pattern can be measured by using your nose. Okay. Now the Wi-Fi has become suitable solution because of its bandwidth, because of its coverage, because of its penetration, and because of the transmission power. Now there is in one Wi-Fi router can reach to my entire house. That's one. Bandwidth anywhere 2.4 gigahertz, 5 gigahertz. A lot of bandwidth is now available. Coverage is there. Penetration is there. It can penetrate even the walls. So that's very important. So, and it is very, very cheap, right? And see, so far we have been using Wi-Fi for data communication. Now we are using the same Wi-Fi technology, same Wi-Fi device for other activities, for sensing also. So Wi-Fi sensing is another dimension in Wi-Fi signal, and that's where we talk about it. So how sensing can be done? I think just now I have explained. At least one Wi-Fi transmitter and receiver are needed for the sensing. The receiver should be able to sense the changes in the transmitted signal. Initially, the system learns the environment with no humans in it. Whenever the system wants to track or sense the human, the transmitter sends the signal to the receiver. The receiver receives all the reflected and refracted signals from the object and human along with the transmitted signal from the transmitter. That's it. So what is the classification of Wi-Fi sensing? I will talk about the first two, and this one in this class, in this talk, will not talk about it. What is the received signal strength indicator? This is there for ages now. In your mobile phone also, you see some vertical lines. That is your signal strength. So signal strength is that if the Wi-Fi router transmits a signal, by the time it reaches a receiver, there will be a signal drop, strength drop. So that received signal strength will also give you some information. You will see that. Channel state information, I just told you that the Wi-Fi transmission happens in multiple Wi-Fi channels, wireless channels, and each channel has an information. What is the amplitude? What is the phase? What is the PSK value, etc. So this channel state information gives you a minute or a small granular information. Received signal strength is only one value, but channel state information will give you hundreds of values. Those hundreds of values can give you information about the activity of the human being. Wi-Fi radar, I will not talk about this because we require software defined radar and etc. Now, as I told you, why Wi-Fi? As I told you earlier, since Wi-Fi is easily available, it's already there indoors, it is there in outdoors, it is there in railway stations, it is there in playgrounds, it is there in stadiums, it's almost everywhere now. You don't have to install it separately. Wi-Fi is universally adopted standard, so the standards are very easy. And Cisco predicts that by 2022, there will be around 549 million, a million equal to 10 lakhs, right? So there will be around 54 crores public Wi-Fi hotspots. It's almost will be everywhere, it will be there. Wi-Fi hardware is produced very low cost, etc. And most importantly, the signal passes through the walls and other objects. So you can, it doesn't require line of sight. That's also an important thing. I think this slide, I can only talk about this part actually. This is very important. Wi-Fi allows me, or the wireless communication of the IoT part allows me non-intrusive. That means you don't have to insert anything in your body, or you don't have to, and device free. You don't need a separate device for this. Remember here, I'm not wearing any sensor. I'm not wearing any device. I'm not inserting any pin or needle, etc. It is a non-intrusive, device-free sensing. So that's very interesting here. The interesting part is that I will do the way I'm doing, and I'll go to toilet, I'll go to restroom, I'll complete my activity the way I'm doing. But the Wi-Fi router and the receiver will be able to predict, estimate what kind of activities are going on without capturing an image and all these things, right? So this is the new term actually, device-free wireless sensing. So the device-free wireless sensing, in the sense that so far we have been talking about IoT devices. Now we will be talking about no device, only the communication. Wi-Fi, the communication is happening. We'll measure device-free communication means I'm not talking about Wi-Fi router. I'm not talking about Wi-Fi receiver. I'm talking about designing a separate device to be weird or to be put up in the human body or something. You do the way you are performing your activities, and the Wi-Fi sensing, which is there omnipresent, will try to do it. So even if the person is non-cooperative, for example, if you want that it should be a device, he should wear it, he may not wear it, or she may not wear it, right? So they may not cooperate. The example which I gave, the pregnant ladies didn't cooperate to wear the belt to monitor the health of the baby. So that's a challenge. So now you don't have to do anything. If I can, of course, that's a big dream. But if I can design a Wi-Fi sensing model where you don't have to, the lady doesn't have to wear any device. It is there whenever they walk in the ground or come to the hospital, etc. The Wi-Fi sensing will sense it. Now, those kind of research that is being planned these days, and we'll just talk about these things. Sorry. The last point is that if you look at the state-of-the-art technique now, the sensing technique now, like camera or wearable sensors, the device-free wireless sensing does not require specially deployed sensing techniques. It also works in dark, because while you don't require light, for camera you require light, for sensors you require a good environment. Dusty environment, the sensor doesn't work. Wi-Fi is independent of light, independent of dusty environment, independent of everything, right? So it really works well if you can make it work. So I think this is the same thing that I've been trying to do. Okay. Now this, you look at this, the RSSI based Wi-Fi sensing. RSSI means what? Received signal strength. A transmitter will send the signal, like in any wireless communication. The receiver will receive the signal and then collect the data from it. Now I'm trying to go little lower MAC layer. I'm not looking at the data. I'm looking at the signal characteristics. So whatever data you send, in fact, one good thing about it that you don't require a password or a authentication mechanism here, because I'm not looking at data. I'm only looking at what is the signal that is going on, right? And what are the characteristics of the signal. If the characteristics of the signal, I can train it that if this is the characteristic of the signal, this is the model, this is the activity. If this is the characteristic of the signal, this is the activity, and that's it. But received signal strength gives you only one information. What is the strength of the signal that receives at the receiver end? It doesn't give you much information, but still you can see. You read the last paragraph. When this technique we use for counting number of people moving inside a room. We did a very small experiment. So again, I'm saying it's a IoT model. But the IoT model, I'm not using the sensors in my body. I'm using only the communication part of the IoT to go for the sensing. So when a person moves inside a room, there is a multipath change, right? Reflection, etc. will happen, and the received signal strength value seems to be fluctuating and may not give you enough information for activity recognition. But you can find out how the person is doing. Now look at this. This is a small experiment which we conducted inside the lab. So if you look at this, there is a RX means receiver, TX means transmitter. So this is the lab, and this is inside the lab. There is a 10-feet lab actually. So people come in and people go out. Now when these persons come in and person go out, there is a lot of look at this line. So there is a reflection here. When it goes here, there is a blockage. When it comes here, there will be another reflection. So and then it goes to the wall and there is a reflection, etc. So when the people move around inside the room, the strength of the signal that is received at the RX, that is the receiver, will changes actually. Now we'll see what you are doing. Now look at this thing. Okay, I'll go back to that. Now here, what we did, we look at this. The experiment is conducted for around 8 minutes with 5 people. I have 5 students actually. They walked in and walked out actually. So experiments were conducted for around 8 to 10 minutes. So 5 students were there. They come in and inside they move around the room and then slowly they leave also. So they through the communication area, entering and exiting one by one with an interval of 30 seconds. So first I asked one student to get in, and then after 30 seconds another student, then another student, then they move inside the room, and after that one by one they leave the room actually. Now what we did, we collected the RSSI in the y-axis and plotted it. Now the time is in milliseconds, that's in the x-axis. Now look at this. The RSSI value change actually. How the RSSI value changes actually. So because what happens, you say that why it is increasing? It is not increasing actually. It's in the minus side. If you look at this, the x-axis is in the minus side in the dB. Now look at this. When there are 5 people, first there is nobody here. Then one fellow entered, then 2 fellow entered, etc. When there were 5 people, I found the peaks like this. When there are 3 people, I find the peaks like this. Here also there are 5 people. So as I told you, if you go back to this logic, right? No human being here, no student, no person here wearing anything. What is that? There is a Wi-Fi router in my room, and there is another Wi-Fi router there is one computer which I use as a receiver. I collected the data there, and then the people started moving, etc. And it's a simple experiment, right? We just created received the signal strength and then plotted it. Now looking at the plotted, I can find out that how many people are inside the room actually. So what is that we are doing now? Let us say from the receiver, if you send the data to a mobile phone or something, right? So I can see the plot here, and this plot here, I can say that okay, there are 5 people here inside the room. I'm not going to the room. There is no camera in the room. There is no extra device in the room. No person is wearing any extra devices, etc. But still, you are able to do it. How we did it actually? If you look at this, we used I think many people might be knowing it. We used a simple ESP8266 module for receiving the signal, and that's it. So we use 2 ESP8266 module. One is for transmission, another is for the receiver, and the distance was 10 meters. We took around a 30-feet room. So in the 30-feet room, we did all these things. So initially, we set up a Wi-Fi device, that is ESP8266 node MCU, for collection of the RSSI values for people counting. Now experiments were conducted for 5 people, as I told you, for 5 people walking through the communication area. Data is collected with a sampling rate of 500 milliseconds for around 8 minutes. And this is what I'm trying to tell you, that this is how we could count the number of peoples. Although I'm not saying there is no error there, But you see, when you say that there are around 20 people inside the room without any camera, without anything, that 20 may be 21 or 19 or maybe 18. So we may not be able to exactly tell what is the number of people there, but yes, we are able to tell whether a person is there or not. That's very clear, because here, if you look at this, when there is nobody, the RSSI is very stable. But when people enter and move around in the room, then it starts fluctuating. Now here there is a 2%, and then 3, and then 5. So I'm able to predict that, and there are some errors, 1 or 2 error are there, like the 5% will become 4% sometimes, but then I'm able to tell how many people are around that. Look at the experiment is very simple, but still we are able to compute it, train it, and then find out that, okay, these are the 5%, etc. Now, let me tell you what is a CSI value. The CSI value, that RSSI value is like I'm just giving a small example. There is no prism actually, but I'm giving a small example. RSSI gives me a value of a single information, right? But actually, if you know somebody who has worked on wireless communication, etc., in IoT domain, you know that the signal is getting transmitted in sub-carriers, sub-channels. So there are many channels, but the 2.4 gigahertz channel actually gives you 30 sub-carriers. So channel 1, channel 2, channel 3, channel 4, up to 30. So this is what is called a sub-carrier. Sub-carrier 1 to sub-carrier K. That K is actually normally 30. Right? Now this CSI value, CSI means channel state information, is like you get 30 values for one transmission. If you get one transmission, you get one RSSI value. The RSSI value is equivalent to 30 channel state informations. That is what we are trying to do. Now, instead of using RSSI, because with RSSI, I'm not able to detect the human activities. I'm only detect that there is a human being. But whether that guy is jumping or waving or sitting or falling, so that I'm not able to detect. So we are trying to use the CSI values. We're trying to use the CSI values for the activity recognition. So the CSI, that is the channel state information, is used to capture fine-grained variation in the wireless channel. Even if there is a small change in the wireless channel, the CSI value will change, and that change you can capture, and then you say that, okay, this is what is the activity. CSI is the strength of individual subcarriers. I repeat, these are the individual subcarriers, 1, 2, 3, 4, K, up to 130, individual subcarriers. The main challenge in CSI-based approach is that accessing CSI data in commercial devices is difficult. In fact, the first challenge was that how do I get the CSI value? Then we did some study and all that. We found that there is a module called Intel 5300N. I'll show it also in the later slide. That helped us to capture the CSI value. And I tell you again, and I repeat again, CSI value has nothing to do with the data. Whatever data that is being transmitted is not my concern. My concern is that I'm only looking at this signal. So with the help of CSI techniques, we can do more accurate localization. That means where that person is there inside the room, whether he's sitting on a chair, whether he's standing nearer to the door, whether he's standing nearer to the almirah. So all these things can be accurately localized. You can track the object, and you can also calculate what is that activity. Now see here, what is the basic idea? The basic computer science model here is that you get, say for example, as I told you, this is the transmitter, this is the receiver, and then there is a furniture, there are human beings, there are so many things in your room, right? They get reflected, and you get it here. So the channel state information will be collected here. Once you get the channel state information, that is my input to the program or to the model. Now, of course, there will be a lot of noise, there will be fans, there will be ACs and all these things, and there will be outdoor noise, etc. So the noise filtering, noise reduction, etc. will be done. So I have a colleague here in electronics who helps me in the signal processing part. I don't work on signal processing. So then it will be clean. Once you clean it, you get clean channel state informations minus the noise. There will be a bit of noise, but that is okay. You can ignore it by considering it as an outlier. Then what happens? We talk about algorithms. We talk about deep learning based algorithm. We talked about other machine learning algorithms. So these are the algorithms part of it. So which I discussed at the beginning of it. Then what is the application? I can do detection. Yes, there is a human being. He is doing this. I can recognize also. I mean, this we have not done yet, but we are trying to do it. A PhD student is working on this. So we are trying to recognize also a particular human being. Let's say the activity in the sense the way you walk, the way you sit, the way you raise your hand, etc. Right? This is a typical signature of a particular human being. So I would like to know, I mean, we are conducting an experiment that if somebody enters into my loop, out of my 5 students or 6 research students, can we characterize who is that guy who entered into the room using the Wi-Fi sensing, not using the camera or something like that. So this is, but detection we have succeeded. Recognition we are still working. Now, okay. Now there are a lot of issues here actually, because the material that is there inside your room will detect the will find out the will change the pattern actually. So when your training is happening, you should train it with different type of material, with different type of rooms. Your cement will have a different reflection, wood will have a different reflection, light will have a different reflection. So many things are there actually. So that's what I'm saying. We are trying to sense these 3 things: whether the guy is there, detection, where is it, this, and then what is he doing, whether he's walking, whether he's sitting or something. So this is what is basically sensing human beings without using any wearable sensors or anything, just using the wireless communication part of the IoT, and then you do it. Okay. Now let me talk about how much time I have. Do I have another 10 minutes or so? 10-15 minutes? Dr. Tiwari? Hello? Anybody can tell what is the time now? Okay. Hello.
Sir, it's 11:10, sir.
Okay, so I have 11:10. I have a time up to 11:30, right?
Yes, sir. Yes, sir. You can extend it for 5 minutes or 7 minutes, because I have scheduled the next lecture from 11:45.
No, that's okay. 11:30. I should be able to complete within another 15-20 minutes. Yeah.
So yes, you can extend it up to 10 minutes if it is required.
Thank you, sir. Thank you very much. Thank you very much. I'm sorry, I'm not wearing my watch actually. So the experimental setup for human activity, how we set up the experiment. The data set contains CSI values of 6 activities. So we conducted experiment with walk, jump, fall, clap, sit means no activity, just sit down, and wave your hand, kind of a thing. Now around 9 participants with MTech students, etc. And this we collected the data set also. So for 8 days and 9 participants, the data was recorded for 1,000 trails in each activity, and the trail is done for 5 seconds. So there are 1,000 such data. That means falling around say 150 or so activity, clapping around 150. So for 5 seconds we say start, and for 5 seconds that guy will start waving or falling down or jumping, etc. So we collected around 1,000 trails have been collected. So we used a Raspberry Pi. I think some of you might be knowing Raspberry Pi is another controller that is used in IoT for quite some time. So Raspberry Pi is there, and normal computer also. Raspberry Pi I'm using, even normal computer can also be used. So Raspberry Pi is used for transmitting the signal, receiving the signal, etc. We use OpenCSA platform. There are some libraries available in C and C++ also, MATLAB also. So OpenCSA platform we have used to collect the CSI values and characterize them. Communication was done with 2.4 gigahertz frequency. Now you see the routers are coming with 2.4 gigahertz and also 5 gigahertz, but we have done with only 2.4 gigahertz frequency. We have not yet done with 5 gigahertz frequency, and we don't know how it will behave. Probably it will behave better in 5 gigahertz frequency. The transmitter and receiver as of now is we are putting at 2.5 meter. 2.5 meter means it's almost 10 feet. Almost 10 feet distance. So I put a transmitter at one end, and another 10 feet I put the receiver, and within this 10 feet I conduct the activity so that you can find out what is that I'm doing. Now, yeah. So this is my setup. So this is the Wi-Fi router, right? It's there in the room, and this is the Intel N5300N card actually. So that is put inside the desktop. So this is my desktop actually. Now what is there? There are 3 transmitters: transmitter 1, transmitter 2, transmitter 3. There are 3 receiving antennas: antenna 1, antenna 2, antenna 3. So 3 transmitters, 3 receivers. So what are the number of combinations? 9 combinations actually. Transmitter 1, receiver 1, transmitter 1, receiver 2, transmitter 1, receiver 3, like that. So this is the setup. Now, what are the observation, the results? How do I observe it actually? We observe that each activity, what are the activities? Jumping, falling, clapping, sitting, and all these things is behaving abnormal when compared to the other activity at some point of time at a particular subperiod. Now, this is important. Why we did all this 3 by 3? Because see, when I do a walking activity, the channel state information is not changing for all parameters actually. Maybe the channel state information corresponding to transmitter 2 and receiver 2, there is a small change, but other they are not changing. So that is very important actually. So we conducted 3 transmitters, 3 receivers, And in each transmitter receiver pair, there are 30 channels. That's what I said. So I have 3 transmitters, I have 3 receivers, and this, let's say 1 to 1, I have 30 channels. Here also 2 to 1, I have 30 channels. 3 to 1, I have 30 channels. Similarly for the other things also. So what you do, you observe that each activity is behaving abnormal. We find that there is some abnormality in the CSI values for a particular set of transmitter receiver and in a particular carrier. And now if I can do that, if I can recognize that, first is that we did it manually to look at that how it actually behaves. Then we use the algorithms. So activity doing nothing means simply sitting is taken as the reference. So we say that when the activity, when the guy is sitting coolly, you take that as the reference point and no activity, that's considered as no activity. And then you conduct the activity and the data is conducted like this. What is this? 3 transmitters, 3 receivers, 30 subcarriers, that means 30 channels. So that is one frame. That's like a photo. Now within 5 seconds, because you conducted this experiment for 5 seconds, right? So within 5 seconds, I just collected this 100 such records. So 100 frames. So 100 multiplied by 30 multiplied by 3 multiplied by 3. So 2,700 samples you get, and each sample we found it for the one particular activity. Now we conducted that for 1,000 such activities, 1,000 such conducting. So you have a huge amount of data. Now this data we try to train it so that you can find out what kind of activity is going on. Now this is just for a small example. I'm saying activity is fall. Channel is 5. Channel is 5 means there are 30 channels, right? In the Wi-Fi communication, there are 30 channels. That's what OFDM. So in channel 5, we find that for transmitter 1 and receiver 1 pair, from transmitter 1 to receiver 1, transmitter antenna 1 to receiver antenna 1, in channel number 5, if you plot it, if you plot the values, you see this red line is now no activity. That means the guy is simply sitting. I collected this. This is the red line. Now at some point of time, when the guy falls, I find that there is a big jump in the CSI value. Why this? Now you say that why it is not here? It is not here means because, say, when you say you fall down, right, within 5 seconds, so that guy takes some time and then falls down actually. So when he falls down, actually we found this activity, right? We found a kink in the signal, in the CSI value. So that gave us confidence that okay, there is a change in the CSI value at channel 5 and stream 1 is to stream 1 means transmitter 1, receiver 1. When you go for jump activity, now look at this. This doesn't change. This is my no activity, simply sitting. When this guy jumps, right, he will jump a couple of 2-3 times. So these are the jump times. So this guy means he's jumping inside the room. But look at this, stream 1. But I found this, sorry. I found this activity, I found this pattern at channel 10, not in channel 5. Channel 5, we didn't find anything significant there. Similarly, walk activity, you continuously walk inside the room. Look at this. Look at this. This guy is continuously walking, right? So this is channel 15. We found that at stream 3.1. What is 3.1? Transmitter number 3, receiver number 1. We found a clear distinction. In other cases, we could not find clear distinction. Similarly, for clap activity, for wave activity. So we did all these things actually. Now what we did, but you cannot always look at the graph and tell you what is that. You have to have an automatic algorithm for that. So what you do, we implemented a deep neural architecture. We used, as I told you, I used AlexNet, I used QuizNet, I used so many things. I also use convolutional neural network principle, right? This is the deep neural architecture. I didn't talk much about it because we didn't have enough time for that. And I don't want to spend more time on that actually. So we need CNN network for training the CSI based human activity. This network, we have 15 layers of CNN. 15 layers, you imagine 1, 2, 3, 4, up to 15 layers, and they are fine-tuned for the parameters for the better accuracy. That's what I'm saying. I used deep neural network like VGG19, MobileNet, ResNet, Inception V3, and followed the transfer learning approach. I think I told you at some point, we follow the transfer learning approach because I cannot do the training for another 6 months, etc. So I used a trained model, and that trained model for some other application, I use it for Wi-Fi sensing. And in the Wi-Fi sensing, I change it. I just fine-tune the training such that it recognizes my activity. The training time was high initially for 40 minutes, etc. But we reduced the time by looking at something else. Now we trained the whole network without validation. Initially, we just tried that. Then we considered 150 instances for every activity. Jumping, we had only 90, but Okay, now look at this. What we did, people who understand this, first we found, we trimmed the activity. Now look at this, 80 to 270. What is this 80 to 270? You remember I said 100 multiplied by 30 subcarriers, multiplied by 3 receivers, multiplied by 3 transmitters. Now this 100 we have reduced to 80 because initially we trimmed this actually, because when you start the activity, you don't do it initially actually. So first 10 records and last 10 record didn't have any information, so I removed it. So I considered only 180 frames, and this 270 comes from 30 into 3 into 3. But that took a lot of time, but that's okay. So if you consider only 50 and only 49 out of that, no, not 270, I used a PCA, principal component analysis, and chose only 50 of those parameters, 270. Then the accuracy was around, falling was around 85%, walking was around 92%, and these are the values. Nothing is nothing, right? It is almost 100%. But imagine when you as I told you at the beginning also, if you give more data, if you give voluminous data, the deep learning gives you a better performance actually. So when I gave the complete data, 80 by 270, look at the values. It's almost 98%, 94%, 92%, 94%, 98%. So earlier it was 80 to 85%, 77%, 92%, etc. But now it is increased quite a bit actually. So if I look at this, then what we did a small experiment. We said that, look, what do you do with only activity recognition? For example, walking, waving, clapping, etc. We thought that, in fact, we changed our goalpost. We changed our objective a bit. We said that, look, I want to say that falling is the important activity for my parent. So I don't want them that they should fall down. And if they fall down, I must get immediately a message in my, even if I'm there in my bedroom or drawing room. If they fall down in the restroom or toilet, I must get an immediate message. I don't know whether walking, waving, clapping, etc. are good or not. I have no problem with that. So one particular activity, let's say falling, I want to see that there is no false negative. There is no false negative in the sense that if they have actually fallen, it should not say that it is some other activity, or it should not miss that falling activity. I'm okay with some false positives. What is false positive? Suppose he will not jump anyway. My father will not jump anyway. But anyway, if he is walking or jumping, and by mistake it gave me a falling signal, once in 1,000 cases, it's okay. Or once in 100 cases, it's okay. But I don't want to miss any falling activity. So that means what? The objective, I changed it that to minimize the false negative of each individual activity depending on the requirement. For example, I don't want to, false negative means what? False negative means the guy has already fallen, but you say that he has not fallen. So that's a false negative. The guy has not fallen, but you recognize it as a fallen. That's a false positive. But I said that little bit of false positive is okay, but false negative should be minimized. That's my modified objective. And then we did a deep learning technique, etc. So what you propose here, or what is the research component here? I think many people have started working on it. They say one deep neural model or one deep learning model is not good enough for this. So what you did, we considered all these models, right? With this mobile net, Inception, ResNet, VGG, etc. So what is the idea? How I arranged them? I found that for this particular application, mobile net gave me better result compared to Inception, compared to ResNet, compared to VGG. So what I did, first I took my sample, right, and I gave it to the mobile net. The mobile net prediction will be whether it is fall or not fall. If it says it is a fall, I say okay, it has fallen down. So immediately I get a communication message that my father has fallen down. If it says it has not fallen down, right, it's some other activity, but I'm not very sure. This might have missed it actually. So this model might not have recognized it properly. So we say that even if it is negative, you give it to the second model. So the second model will again predict whether it is fall or not fall. If it is fall, again you accept it. Otherwise, you go to the third model, fourth model. What we found that is very interesting. What we found that even if you missed a fall activity in the first model, subsequent models is able to tell that it's a false. It's a fall actually. So any one of the model, if it says fall, it's a OR approach actually. If stage 1 or stage 2 or stage 3 or stage 4, if it's a fall, it's a fall. Otherwise, we say it's not a fall. Now, if I do this model, I found that so it's a multi-stage deep learning model using different popular models. The activity is classified as negative only if this is ALL. This is ALL. Only if all the models classify it as negative, otherwise it is classified as positive, right? So if you look at this, this is the confusion matrix. the confusion matrix says that there are output classes: clapping, falling, jumping, nothing, walking, waving, etc. And then we try to see that now look at this actually. Initially, this is the initial model actually, the first model. First model says out of 150, clapping is recognized as clapping as 130, but there are the same clapping activity is also recognized as what is that called jumping activity. The clapping is recognized jumping activity in 17% cases. So that was a little bit of wrong, but we try to improve it, and then you find that look at this. Look at this. Once we did the confusion matrix for this multi-stage modeling, that 130 became 147. 147 means there are total 150 cases, 147 is recognized as correctly. There is no false. And so the false negative is reduced to only 3. Initially it was 20. Then it was 149, almost all falling activity, I repeat, all falling activity except one was recognized as a falling activity only. So 150 times that guy has fallen for test case. 149 times we are detecting it as a fall activity because we go for the multi-stage deep learning model. Only one case we could not detect it as a falling. That's only the one. Now it is reduced to almost 0.1% actually, right? So 99.3% accuracy we are getting in a multi-stage model, but only look at the last column, 99.3%. So the 99.3% is the accuracy now for fall activity, and that's quite good actually. So so if I look at the idea is that in a single model, that means if you use a single model, you get 3.9% false negative. For 3.9% false negative means almost 4% cases I'm missing it actually. The falling is identified as some other activity, and 2.0% is the false positive. That means some other activity is identified as a falling activity. But in a multi-stage model, we almost reduced it to 0%. So 0.7%. I think you have seen this, right? 0.7%. This is the 0.7%. So similarly, we found out all other activity, walking activity, waving activity, etc. In all cases, if you find that 3.9, 1.4, 5.9, 3.5, 18.6% in jumping. That was a quite erroneous thing actually, because this jumping, these people are jumping and walking, jumping and standing, jumping, and when they jump, actually they jump and then they sit. So that sitting is recognized as a false, as falling. So we had 18.6% probability there, but that was also reduced to 4.4% only in case of what you call multi-stage activity. So the false negative is reduced to 1.1% from 4.8%. If you look at the average, it's now 1.1% only. So let me conclude. We tried to present a sensing without sensor model using Wi-Fi signals. We use RSSI values and CSI parameters to model the problem. Preliminary experiments results to count the number of persons, basic activity detection, gestures, etc. are actually working fine. I mean, we are able to do that actually. In fact, I have another slide, but another experiment, but I will not talk about that. I will only tell you what is this actually deep learning for gesture recognition. Gesture in the sense what? If I show my hand, right, go. I will not tell you, just I wave my hand, go. So what we try to do is that can we also recognize the gestures? Gestures in the sense the language, body language, your movement of the hand, your movement of the finger, etc. Can I find out that? Some people have done some gesture work earlier also, but what we did, we thought that we will not use the normal gestures. We will try to recognize the alphabets and digits. For example, if I move my hand as A, it should recognize that I'm trying to write A. So in A, I'm writing A, and it will recognize it as A. In A, I will write digit 1, it will recognize as 1. The motivation behind this, in fact, we started this work in the COVID period only. The student was there at home. So we said that, look, when you go to the lift or something like that, I don't want to touch. So if you go for a touchless entry, then I should be able to recognize the gesture. Suppose I write 7, then the lift will take me to the 7. That was the idea. Now, I will not talk about more about these things. If required, I can share the slides, but I will show you one video. Yeah. That will give you, because the same idea is same. We collect the data, we use the deep learning model, and so this is the deep learning model, and then we try to do this. But look at the video actually, that will give you. Yeah. So I'll stop here a bit. So what is this video about? This person is waving the hand using a IoT device. Actually, this is not Wi-Fi sensing, by the way. This is IoT device. So you wear it as a Fitbit device or in your finger or something like that, and it is in his home because he did it in the COVID period. So what we are trying to do is that he will try to wave his, move his hand, move his fingers, and then the system will recognize what is that he is trying to tell. Whether he's trying to, and I remind you, there is no camera here, there is nothing, only the movement. The movement will be detected by the sensor, and then that will be recognized as what is that he is trying to tell. And you will find that at the top right hand corner, you will find that there are two symbols. One is that what is the signal or what is the gesture, and what this system has recognized. And there are some errors also, you will see that. See, this guy has written 3, and the system also recognizes 3. Who is the system here? The cloud, actually, this server. So the signal will go to the server, and the server has classified it using deep learning algorithm. Now we are testing it. Actually, the guy comes and puts the testing, and then you find that he has written 3, and this is also written in 3 over here. So now see that. Three is recognized as 3. Now see, he's writing H, but it is recognized as 4. That's an error. But now he will done it again. H is recognized as H. He wrote X, Y, but it is recognized as X. So these are the 2 errors actually I wanted to show you. Now Y is recognized as Y. This is Z. This is X. This is N. N. M. Yeah, this goes on. E. F. S. Eight. Now, why you are doing this? Because when you do this, your gesture is recognized as your command, and then you see it. So what we did, we collected the data with the different students. We used some 10 students, and they do all these things, and everything is collected with. There is still a lot of work to be done because we did it with only right-handed people, and we are not using any old person or new person. All of them are students, so the experiment is still on. So again, what is that we are trying to say? 3,600 or 10,800. How do I get 10,800 samples? 26 alphabets plus 10 digits. So that is 36. Now 36, 10 people. So this will be multiplied by 10 people. So that is now 360. And for each one, we collected the data for 30 instances. So that becomes now 10,800. But if I say that, okay, if I take the data set to be only 100 or 1,000 or 3,000, so what is this 3,000? 30 multiplied by 10 multiplied by 30. So if the point what I'm trying to make it here, that I have 10 digits and 10 students. So if you take 10 into 10, only 100, that means the accuracy is only 52%. But if the same students gives me the data for 10 times, then it becomes 1,000. Then it becomes 96.6%. When you do it for 300 times, then it becomes 98.67%. What is the idea I'm trying to tell? The deep learning is that if you give more data, the accuracy actually increases. That's what I'm trying to say. So we have used 80% data for training and all that. Now this is for the alphabets. 226 alphabets, 10 students. So only once they did A, another time they did B. So if I take this 260, the accuracy was only 64%. Why it is so? Because in the digits, actually, there are a lot of overlaps, actually. This 3 and 8, 7 and 4. So there are some overlaps. So that is why the error was little more. If you do this same experiment for 10 times, every student will do it for 10 times, then the accuracy increases to 98.42%. If every student did it for 30 times, the accuracy increases to 99.29%. Why? Because we have a lot of data. So now what we did, we mixed both in this table. We mixed actually both 26 alphabets plus 10 digits. So now it becomes 360, 3,600, 10,800. Now the whole idea is that we get around 98.52% accuracy. How a student comes in, uses the device and makes a gesture in his move, just signals 3 or 4 or A or B or something like that. Now there is a issue here because O and 0, they are all same. So how do I distinguish between O and 0? As of now, what we have done, O we are writing clockwise, 0 we are writing anti-clockwise. So that's how we try to break the tie here. So that's what I'm saying. There is a work actually. This gesture keeper work is so far the best work actually. So they have used all these things. They found only 97.89% accuracy. And of course, that's not a big deal. And we found out 98.67% accuracy. But the problem is that their number of classes were only 12. We have used for 26 alphabets plus 10 digits. They used only for 12. They could not go up to 36. Even if they go up to 12, went up to 36, we can still classify it up to 98.61% using the convolutional deep neural network algorithm. They have used hidden Markov model, right? So as of now, we stand here actually. So that's it. I mean, I don't want to. What is that I'm trying to say? This I said digit 0 and alphabet O. So we did one as a clockwise and the other one as a anti-clockwise. So all said and done, I think I should conclude here. I must acknowledge my students. A couple of my students are there. Ajit is a PhD student. Shruti is a PhD student. Somaya, Mutunjay, Pragya, they are all my master students, did internship with me. So thank you very much for your time and for listening to the talk. I'm done.
Thank you, sir. There are a few questions. There are a few questions from the participant side, sir. So I'm just just repeating that one. One question is from Aditi Raj, and she's asking how you decided upon the number of transmitters and receivers and convolution neural network layers. And at the same time, she's asking that how did the performance accuracy increased in case of 50 cross 49 for nothing from 98% to 99%?
Okay, I'll go back to that. There are two things here. First part of the question, how we decided about 3 transmitters and 3 receivers, right? So in fact, the routers that are available with us, we had 3 transmitters. That router, we had three transmitters, and that Intel 5300N, that card which we use for the receiver, also has three antennas actually, receiver antennas. So this is 3x3. That's pretty simple. So we didn't have to struggle much there. If I have to go for 4x4, that means there are some routers with 4 antennas, then it becomes 4x3. So the experiment what you have conducted is using 3x3. That's the first thing. So the choice is that the availability is the choice. We didn't go for any new devices or something. What was the second question? How do you decide about the layers and all these things? I think you missed that point. I said that I use transfer learning approach. So the transfer learning approach, I said VGGNet, SqueezeNet, AlexNet, etc. Some people have already done that research in image processing, audio processing, etc. I use that network as such. I didn't train it because that training will take 6 months. So I didn't train anything. I used that network and then used that. I mean, just implemented the algorithm with this data set. And the third question was, I forgot.
Sir, third question is, I am again repeating it. How did the performance accuracy increase in case of 50 cross 49 for nothing from 98% to 99%? I think she's talking about some data which you have presented from your experiments.
Okay. Let me go back. I think this slide you are talking about.
Aditi Raj, you can unmute yourself and please respond. Aditi Raj, if you are here.
Yes, sir. I'm talking about that slide. So in case of nothing, when you're using less number of data points, there I see 99%. However, you have used more data points, it's 98%. So there I got a confusion.
Yeah. Of course, there is no confusion actually. The confusion here, I mean, I can understand this. So the 99%, 98% is actually very close actually. In one case, with 80 to 270, when you say all these results, I'm presenting you an average of 5 runs, right? I'm not talking about one particular individual. So the average of 5 runs, average of 10 runs, I'm putting. So nothing is basically I'm sitting, I'm not doing anything. Now, some of these activities of sitting and not doing anything is classified as some other activity. For example, this guy must be sitting and not say, I tell you very honestly, actually, we didn't ask them to do the activity as we want them. We asked them to do the activity as a normal one. So that guy must be sitting and probably waved his hand or something like that, or changed his hand this side or that side, or moved a bit here and there. So that was active. That was probably, and that was probably captured as some other activity. Maybe just 1% cases like that. But otherwise, this and again I tell you, I just rounded it up. Actually, it is not exactly 99%. That may be 98.6%. This may be 98.4% or like that. So I just rounded it up.
Okay, sir.
Okay.
Thank you, sir.
Thank you very much. Anything else, sir?
Okay, sir.
One
Thank you.
more question from Asmita. She's asking that how performance increases with high amount of data.
Okay.
I think she's asking in the deep learning scenario where you.
I know. See, the deep learning model is designed in such a way that with more data, it gives. That's what the first thing I said. In a multi-layer neural network, in standard SBM or other machine learning algorithm, even if you increase the volume of data samples, it doesn't increase. The accuracy doesn't increase. It becomes flat after some time. But deep learning actually, because of its multi-layer neural network, multi-layers, feature extraction, feature, etc., the more data you give, it is able to extract more features and accurate features. And that is why it is able to increase the performance. And that's the key actually. That's the beauty of deep learning algorithm. More the data samples you give, the accuracy increases. That is why people are stuck at 85%, 75%, etc. previously. Now suddenly everything is 90 plus. You talk about character recognition, you talk about voice recognition, you talk about image processing, everything is now 95 plus with deep learning and all these things. It's basically due to better extraction of features.
Yes, actually, what sir have said, that it is the part of the deep learning that it is very new in this field, and in machine learning approach, you would require less quantity of data. But when the data size increases, then deep learning perform much better in comparison to machine learning because it learns automatically, and no human intervention is required in this. So it is the feature of the deep learning tools. So you can read it more in the literature from deep.
Yes, sir. Yes, sir.
And
Very
different good research papers. So thank you, sir, for your such a good informative sessions. And people, sir, participants and faculty members are writing it that they have learned a lot from your sessions.
Thank you very much.
Nathan,
Yes,
sir,
sir.
please.
Yes, sir.
Yes.
Thank you, sir, for your wonderful and informative sessions. Thanks to you, sir. Now I request Professor Pawan Kumar Tiwari, sir, for sharing the token of appreciation to you. Sir. Over to Pawan, sir.
Okay. Just it is taking 1 minute. So, sir, this is the token of appreciation, certificate of appreciation from our side, and we will send it. I think the PPT is visible to you. My screen is visible to you. We will send it by post to you on your departmental address. Is it visible, sir?
I think his video is paused. I think network issue there. Dr. Pawan, message.
Is it visible, Dr. Nathan?
Yes, yes.
My screen is visible.
Yes, your screen visible, and this, I think Udgata sir have a network issue, and see right in the chat box. I lost connection and my mic is not working properly. It was really pleasant.
Okay.
Okay.
Okay. Sir, thank you, sir. This is token of appreciation from our side, and we will send it with the signature, a hard copy of this to your mail, to your department, sir, address. Thank you, sir, for your nice lecture. So, dear participants, we will start the next session in 5 minutes. It is the time, I think, 11:44, and we have given the time 11:45. So, just 1 minute, but you can join it immediately, but we will start in next 3-4 minutes. Now you can leave this session. So thank you.